Sorry, you're muted.
Sorry,
Yes.
Giuseppina, you haven't the microphone.
Okay, thank you, Titi. The second presentation is the assessment of suitability of different point clouds for cyclist road safety. The author is Niam O'Reilly from Technological University of Dublin. Please, Niam, can you speak? And you can try the presentation.
Good morning, everybody. Yes, I'll just try sharing my screen now. I'm talking to you from sunny Dublin here. So let me just hope I can share my screen with you. Are you able to see that?
Okay.
Can you see my presentation?
Yes.
Yes.
Oh, good. I have two screens here, so excuse me. Okay.
Perfect. Okay.
Okay. So first of all, thank you everybody for taking the time to listen to my speech today. I am currently doing my PhD on cycling safety, coming from it with a geospatial perspective. So just to give a background, it is being funded by the Road Safety Authority of Ireland, and some of the surveying companies here in Dublin have provided me with data, one from Murphy surveys, which have given me mobile laser scanning data, and then the second survey company did a drone survey of my study area here in Dublin. So the background motivation, cycling safety, there's huge promotion throughout the world to promote active travel, to meet the sustainability development goals for health, for many reasons. One of the underlying issues of cycling is safety and concerns about safety, and figures provided would show that there's far more cyclist fatalities and serious injuries occurring than, and these numbers haven't decreased over the last 10 years since various initiatives have been implemented. This has resulted in a Vision Zero strategy, which aims to reduce the number of serious injuries and fatalities by 50% by 2030 and by zero by 2050. And in order to achieve these targets, data-driven, evidence-based interventions are required. Part of this ties into the study I'm undertaking, and I've looked at the factors that are contributing to cycling safety and how, as geospatial technologists, we can actually identify and help to understand these. And these are divided down into surface quality, which leads to cyclist collisions, street objects where they can cause cyclists to collide with them, or for visibility, the gradient, and also visibility. These are all factors that contribute to cyclist collisions. In addition, the targeted road safety inspection as part of the Road Infrastructure Safety Management Directive, which has been amended in 2019 to include vulnerable road users, has a list of geometric objects that they recommend are surveyed in great detail, and they recommend using these high-end spatial solutions. So to move on, I used cyclist collision data provided by the Road Safety Authority to identify a number of hotspot locations in Dublin City, and one of these was Portobello Bridge, which I'm focusing my talk to you today. The question I had is, which LiDAR data capture method provides the best solution? We've got terrestrial laser scanning, mobile laser scanning, and drones. So what the study did was it undertook a survey using each of these methods and then compared them to find out which was providing the best solution. The workflow, the normal workflow, point cloud registration, cleaning of the data, removing noise from it, segmentation into different categories or classifications, and then using this to create a three-dimensional model and also a surface. So I'm just going to start off looking at the digital elevation model, which was part of the analysis, was required for the analysis. So the terrestrial laser scanner, even though it provides a much more dense point cloud, it doesn't provide full coverage. So it's not ideal for this type of survey for the digital elevation model. I'm showing also the point cloud of the ground surface from the drone and the mobile laser scanning. The drone survey was done very quickly and provided a really good coverage for the entire area. Then for the actual evaluation of the quality of the road surface, the mobile laser scanning provided a much more uniform coverage of the ground. The drone was it didn't provide enough detail to create a good elevation model for the actual curbs and so on. However, when a ortho photo was superimposed on it, it provided very good method for looking at the actual quality of the road surface at the edge, in particular where the cyclist lanes would be. The terrestrial scanner, which I'm showing here, does provide very good detail about the actual curbs and drop surfaces, which is important when considering road safety. For street furniture, including traffic lights and signposts, I've just provided an example of the type of detail that was provided from both the mobile laser scanning and the terrestrial laser scanner. The terrestrial laser scanner, far more dense, so when it came to generating a three-dimensional model, was far more easy to extract that type of information. And then finally, the generation of the three-dimensional model, which I'm just showing here in this slide, that it provides a very useful environment for undertaking analysis. So the analysis that was taken was using visibility analysis. Now I've used ArcGIS Pro to do that, and in this example here, it just shows the green lines showing where it could be visible. There's further analysis done on this to show which lines, where visibility from the perspective of a car, where they can see a cyclist traveling along a cycle route, which is part of this actual model that I've got here. In this, I've used a driver eye height of 1.05 meters. So the assessment of the LiDAR data capture, the terrestrial laser scanner was good for certain types of the analysis, however, poor when it came to creating a digital elevation model and for gradients, because of the way the actual point cloud radiates out and we lose coverage when we're close to the actual instrument itself. The mobile laser scanner provided very good coverage. However, from a visibility perspective, the actual level of detail captured for buildings would have been poorer quality. The drone provided very good digital elevation coverage when it came to just a general digital elevation model, which was useful. But for street objects and surface quality, it wasn't so good. Okay, so to conclude, the point cloud data does provide a good alternative for road safety assessment. And by combining these point clouds together, it's going to provide the best solution. The outcome, this is ongoing research, and what my research would show is that it's not just using this data on its own, combining it with other information. So the other information which is contained in those cyclist collision reports can provide far more in-depth and rich understanding of the contributory factors associated with these cyclist crashes. So I'm going to finish up my talk now. So thank you for listening, and please feel free to ask me any questions. Thank you.
Thank you, Anhiam. And the next presentation is a remote sensing index for assessing the peri-urban ecosystem services, a case from Tuscany, Italy. The speaker is Elena Barbierato. Elena?
Yes, good morning, everyone. I'm share my screen. 1 second, please. Okay. Can you see my screen?
Yes. Yes.
Okay, perfect. Thank you so much, and good morning, everyone. I'm Elena Barbierato, a PhD student at the University of Florence, and today I'm talking about research carried out with my team about the use of a remote sensing index for assessing peri-urban ecosystem services. Urbanization is a phenomenon that has occurred in many European cities, causing multiple side effects such as urban sprawl and damage to agriculture, as illustrated by the artist Philippe Tastet in this figure. This phenomenon has generated peri-urban areas that are hybrid areas located on the fringes of the peripheries of the cities, and they are very, very important for the urban populations. Before this phenomenon, in these peri-urban areas, we had a very good natural aspects and a good water reserve, like this illustration. And then the urban expansion generated a lot of problems. We have had an increase of the artificiality and the temperature in the city, and subsequently generated the heat waves phenomenon. In addition, we have an intermediate situation such as urban sprawl, in which we have an increase of the degree of the artificiality, but preserving the water reserve. And the opposite situation in the industrial areas, in which we have the heat waves phenomenon, but preserving the natural aspects. The development of remote sensing technologies has made it possible to have information about environmental indices useful to assess resilience and vulnerability in the peri-urban areas. And also, we know that in the literature, many researchers used uncertainty-based model analysis, such as Bayesian model, because they allowed us to treat probabilistically the uncertainty risk. However, despite the increasing effectiveness of remote sensing technologies for use in large-scale environmental monitoring, the reliability of studies based on satellite data is undermined by the uncertainty generated by human disturbance. For this reason, our research aimed to assess residual ecological quality in highly anthropized territories through a resilience index of ecosystem services, combining the remote sensing data to a probabilistic approach that considers uncertainty. The study areas is the urbanized plan of the Florence and Prato city in the central part of the Tuscany region, and the input data were derived from 2 different types of sensors. We have downloaded 12 Sentinel images from December 2019 to November 2020, and 4 images for Landsat 8 images from June to September 2020. The proposed method was derived from pressure state response framework elaborated by UNSU in 2018. And it involves the measurements of 3 categories of indicators: environmental states, anthropogenic pressure, and climatic response. In this slide, we can see our conceptual workflow in which we have the remote sensing data as input. From this, we have calculated 4 types of indices, and then these indices were weighted through a PCR analysis and aggregated using the Dempster-Shaffer rules to obtain, as a final result, the resilience index ecosystem services map. For what concerns the first categories of indicators, we have calculated ecosystem services provision index, ESPI, from Sentinel to image, and considering two different types of seasonal dynamics of the NDVI, the annual mean of the NDVI and the intra-annual coefficient of variation of the same. And then in the second category, we have calculated the normalized difference build-up index. And it is very similar to the previous index because we have considered the same, the mean of the NDVI and the coefficient of variation of the same. In the climatic response, we have calculated two different types of indices, the line surface temperature from the Landsat 8 image. And in this case, we have considered brightness temperatures, wavelength of the emitivity's radiance and the emissivity, and the WET, the tasseled cap wetness index. Assessing and monitoring ecosystem services in the peri-urban areas is hampered by multiple uncertainties and lack of knowledge. And in these areas, we have rapidly changes, and it is very frequent to have the resilient and vulnerable ecosystem in the same location. And for this reason, we cannot describe it today using only objective probabilities, and we use Dempsey-Shafter theory because it derives from Bayesian subjective probability, considers the uncertainty topic, and combines several lines of evidence. In our study, we defined two types of lines of evidence. The first is the resilient ecosystem services supported by the ESPI and the WET results, and the vulnerable ecosystem services supported by the NDVI and the LST results. Taking two assumptions into account, each indicator were weighted through a PCR analysis and then aggregated using a orthogonal sum to obtain a probabilistic, basic probabilistic assignment and to verify our hypothesis. In fact, in the first hypothesis, we have obtained the resilient ecosystem services, and in the second, the vulnerability of the same. These results were aggregated through the Dempsey-Shafter rules to obtain three different types of raster map: the probability of resilience, the probability of vulnerability, and the uncertainty. In this slide, you can see our results, and the box plot shows the distribution of our probabilities, and in these other figures we have the specialization of the results. The resilience of ecosystem services are concentrated in the south and the southwestern of the study area, meanwhile the vulnerability is located in the central part and the north of the study areas. And finally, the uncertainty is absent in the resilient ecosystem services and more present in the vulnerability of the areas. So then we have realized the resilience index ecosystem services using a RGB false colors map in which we have put the vulnerability in red band, resilience in the green, and uncertainty in the blue. And we can see that the vulnerable ecosystem services are concentrated in the central part of the study areas, while the resilience are located in the south part. To better understand, we have choose two different types of spatial configuration. And in the first pattern, we can see that the ecosystem services are more vulnerable, and the main land use is intensive crops. Meanwhile, the second is more resilient, and it is characterized by olive groves and a lot of tree vegetation. And in this box plot, we can have the comparison between our different type of spatial configuration, and the results confirm our hypothesis. And in conclusion, the proposed method allowed us to identify the resilience and vulnerability in the peri-urban areas and monitor the changes in these areas. And the main advantages are that the method is replicable, and the resilient index ecosystem services are a very useful tool for urban and landscape planners. And the future developments are increasing the number of analyzed indices and realizing a temporal analysis, and finally testing this method in other areas, and not only in the peri-urban agriculture areas. Thank you for your attention.
Thank you, Elena. And I remember everyone that the question can you writing in the chat box, okay? So the next presentation is how much greenness can mitigate urban warming, a tentative answer based on thermal data from Landsat missions. The speaker is Tommaso Orusa from University of Torino. Tommaso?
I'm here, thank you so much.
Okay.
I hope you can see the screen without any problem. Give me a feedback, please.
No, it's okay.
Oh, okay, perfect. Well, thank you so much. I'm Tommaso Rusa, and I'm a PhD student at the University of Torino. And now I will present to you this work that have involved also my colleague Samuele De Petris and Filippo Sarvia under the supervision of our professor Enrico Borgogna Mondino. We have tried to answer the question, how much green can mitigate urban warming? And we have analyzed a long time series of Landsat images. Well, nowadays, urban planners and also inhabitants and public institutions are looking for low-cost methods to boost urban mitigation, heat mitigation, as a response of the joint effect of climate change, ongoing global warming, and also the urban sprawl. As we can see from these literal images, we can see that there are many examples in literature that focus the attention of how the green areas can mitigate the effect of the increasing temperature. Well, we have focused our principal question trying to answer what is the extent that we need to have a mitigation, and how long the green areas can have a real mitigation effect, because the temperature globally, not only locally, are rising. And until what time we can see a real mitigation, then we have only an adaptation effect of the greening and no more a mitigation effect. Well, we have many purposes on our research. Principally these three: to demonstrate the new role of free Earth observation thermal data application in urban planning and management. The main core of our research was to develop a forecasting model of how much and until when, as I said before, urban greening will have a real mitigation effect, and then performing more than 30 LST trends analysis per each pixel of the area of interest that we have analyzed, and perform different statistics. I have to say only that the pixels were grouped into two macro classes, the green areas and the urban areas. And we have made for the developing of this model an assumption that the town, in particular the study area was the city of Turin, is a closed system in which green areas and urban areas are challenging each other for space. So this is a forcing that we have introduced in this model to try to give us an answer. And the green areas mitigation also have to maintain the land surface temperature at the actual level that we are observing, so the 2020 year. So in order to have no increase in temperature. The future purpose is to extend the study also to other Italian and European cities in order to give useful, hopefully, tools to the decision maker and not only and the technician. So as I said, the study area is the municipality of Turin. You can see here the border of the city. And I want to remark that the basic idea was to consider the municipality as a closed system. This is the principal aspect of our study. What is the workflow that we followed? The LST process, the land surface temperature, were processed in Google Earth Engine according the Ermida methods. So we have considered LST monthly composite covering the period between 1984 and 2020. The green areas and the built up areas were mapped using the Corinne Lancover, the level 3. And then the analysis that we have performed on it was to calculate the LST trend per each pixel and performing a petit test using R in order to test the significance of each trend. Yeah, the LST were modeled by a first order polynomial, and then the gain and the offset were considered where there is a significant trend. Then for each pixel, each trend were grouping into these two macro classes, as I said before, and we developed the forecasting model assuming a city as a closed system. Here are reported the analysis that we have made, and in particular, we have also analyzed these different maps. And in figure A, just in the left of my screen, there is the map of the breakpoints occurrences. And in the figure B, we can see the map showing the p-value and the gain estimated for the local first-order polynomial trend, performing the petit test. What are the results? Well, in the box plot that you can see, we can see that the gain LST for the built-up areas is higher than the vegetation, as we expected. So there are many studies, as I said before, in literature that said that the green areas has a real effect in mitigating temperature. The box plot report the degrees Celsius per month of increasing. In the two equations, equation A, equation B, it can be easily noticed from the offset that green areas show an average temperature about 4.75 degrees lower than the built-up areas in 1984. Today, the green areas and the built areas as well, the difference is 5.39 degrees, in spite that both the classes have increased their temperature, as we can see from the trends in the slide that I have shown you before. After realizing these, modelizing, sorry, the trends, we try to develop an equation that give us answer about how, in which time and for how long the green areas has a real mitigation effect, and how much area has to be moved, converted to built-up areas has to be moved to green areas to observe a real mitigation. Well, we developed the equation reported in the upper part, the C, where the B0 and the G0 are the built-up areas and the green areas, respectively, at the reference time that I said you before in the study area, to maintain the temperature trend and not observing any increase. TB1 and TG, the expected temperature of built-up areas and green areas, respectively, is estimated by the classes related model of a corresponding LST trend. In the graph, we can see that in the future and gradually, the area of Turin have to be converted a great part in green areas in order to have a real mitigation effect. A simulation that assumes as a reference time 2021, assuming B0 as 8,336.5 hectare, about the 74%, and G as 2,921.3 hectare, about the 26% of the AOE, was run. The graph shows us the percentage of amount of area that the present build-up area has to be yearly converted to green area to compensate the average LST increase, about around 2%. So, and we can see in that this moving from a class to another have to start right now. In the conclusion, we can see in this work that averagely, the LST is increasing for all the classes. The built up show a steeper increase than the green areas. A planning and development strategy based on moving the built up areas and to the green areas could somehow mitigate the average temperature increasing. The mitigation effect based on greenness improvement can be effective for a limited time until 2035. That depends on the potential area that actually can be programmed to move from built up areas to the green areas. The green strategy has no chance to solely face the future LST increase due to global warming. So we can see that in spite of a well-known storytelling, green strategy is not only a limited solution for a limited time. We have also to consider other solutions. It's important only for an adaptation, not only for a mitigation, as we can see from the model that we have developed. And also we have considered and imagine also that no more than 10-15% of the present built up can be converted to green areas, because it's tricky for the urban planners and to convert totally a part of a city in a new one, because there are many rules and also it's very expensive. As I said before, the space between two, how can I create houses, and the other, how to create green areas, are in competition as well. This means that if nothing will globally change, the year of 2026 could represent the moment where other intervention will have to program to face the problem of LST increase due to climate change. Thank you so much. If you have any question, I'm here.
Thank you, Tommaso. Now the next presentation. The speaker is Marcello Maranesi, and the title is MAFIS, Multiply Actors Forest Information System, EOI, Euro Data Cube for Scalable Forest Monitoring Services. Marcello, can you speak, please? The microphone, Marcello?
Yeah, can you hear me now?
Yes.
Okay, and you see my screen, right? Great. So MAFIS is a multiple actors forest information system that has basically two components, natural environment and the urban environment. Actually, we started with the natural environment, and then ESA has asked us, the European Space Agency has asked us to consider also the urban environment because of the importance of cities in our life today. Let's have a quick view to the MAFIS in the natural environment. Here we had two regions, Veneto and Tuscany, where we had two test sites. And we looked at the above ground biomass primarily, and also to some specific events that determined a large area destruction of trees. And for doing this, we have used mainly satellite data in the radar domain because of the capacity of L-band radar to penetrate the foliage and therefore extract information about trunks and big arms, so the major components of AGB. On the urban environment, we have involved a number of other players like nurseries, arborists, agronomists, architects and planners, and the customers have mainly been identified in the municipalities, of course. And the objective of this component is basically to find and demonstrate services in support of local planning and local management, especially to foster the improvement of the ecosystem services. Then let's have a look at the first results. Okay, and another step is about ESA asking us to implement MAFIS on the forestry tab, which is a thematic exploitation platform established already 3 years ago, and on the urban tab. So to take these information layers and merge them with the other activities and the other services offered by these two quite developed platforms. And in order to support the effort on the urban environment, ESA is putting at our disposal a network of resources, which basically means storage and computing resources, and also an environment for let's say enabling cooperation between the project partners, and also allowing the customers and the users to access the results of the project. So on the natural environment, we have combined, as I said, satellite data, artificial intelligence, and in situ surveys together with the growth model. And the information that we have provided is an accurate estimate of forest AGB, and more specifically about the AGB variations, both the growing of the stock and biomass losses, disturbances due to a number of events. Okay, and the third, to monitor also the clear cuts and the selective cutting that create big problems and are not properly monitored so far. This is an example of the AGB product. And here we have on the left August 2016, on the right June 2020, and of course, if we do the delta, the addition, we have the growing stock in each area. As you can see, we have a very detailed spatial resolution. This is instead an example of the clear cuts, and clearly there is the possibility of improving the current accuracy of the perimetration of the burned areas. The cut areas and also the burned areas. But let's move into the urban domain, the urban environment. And just from the previous presentation, we have understood how important the trees are. Whether they are sufficient or not, it's difficult to judge. I think personally that green areas are probably more difficult to implement, as was said, but probably we can use planting trees to improve locally the situation. And trees are basically helping improving the urban resilience, are basically really a kind of natural infrastructure, and support both the ecosystem health and the biodiversity. And not only, let's say, from an environmental point of view, but also from an economic point of view, because urban areas with a lot of green and trees has much more value than other areas. And also from a touristic point of view, these green areas are nicer and attract more tourists. So there is also a direct economic return in supporting planting more trees. What is the project going to do? Basically, we have 3 basic steps. First step is updating of the urban green inventory and the classification of the main species. Here you see that it is not only possible to be done by in situ measurements in the public areas. This is Florence, and you see the yellow dots are the trees that have been sensed, whilst you see how much private green is available there, and any estimate or impact on the ecosystem services cannot neglect the impact of the private green. To do that, we integrate various types of data, aerial, in situ, and also very powerful satellite data, like very high resolution, down to 30 centimeters, hyperspectral, and also radar data. And of course, this would enable to be much more faster in maintaining an updated urban information system about the green areas. Second step is the estimate of the ecosystem services, and specialized model produced by the University of Florence will be used to monitor the tree health status. Here you see an area which is close to my house, and you see that a big course has been completely damaged by illness of trees, and there is a kind of something hurting me every time I pass over there. Carbon sequestration, then removal or reduction, let's say filtering of particulate pollution, assessment of the surface temperature, and also the thermal comfort for people. And another topic that we will be tackling together with University of Molise is the interconnections between urban and peri-urban green areas. So these are important in order to enable animals to move back and forth, and so to keep the green areas in the city alive over time. And the phenological phase is also important in order to predict and support the measures for pollens and allergies. The third step is the monitoring and maintenance of the trees. So the regular monitoring of the trees, and I want to highlight that the availability of Sentinel-2 data allows really to take advantage of very long time series data. So we can reduce the errors by integrating something like maybe 20, 30 images, also comparing seasonal variation from one year to another year. And then the identification of specific targeted actions that needs to be taken. For example, simple tree cutting is something that we have found out that it's quite important, not only for possible danger to people, but also because they interact with the public lighting system and create dark areas that the citizens are complaining about. Okay, this is just to highlight a little bit the various partners and stakeholders that we have, and I would like to thank them all, because we learned already a lot from the left part of the project, the natural environment, where we worked with the GOK, which is Tor Vergata University spin-off, RDM Progetti from Florence, and University of Molise. We have national and the regional stakeholders, also international, like European Environmental Agency and Wood Chain European Associations, and CSEF, the Italian Silviculture and Forestry Association. On the right side, for the urban areas, we have the University of Florence. And actually we selected, because of them and the availability of local data, we have selected Florence as a kind of leader city for this development. Polytechnic of Milan, Super Alberi, which is a small company working really on intervening and on the trees, making the tree cutting and also detailed assessment of their health status, and University of Košice that will support the thermal comfort analysis. In terms of municipalities, we have, you see here, 8 of them, but we are increasing the number of interested cities, like Paris and Lisbon, and also Tirana is adding to the group. Of course, we have also the support from FAO. I'm finished, and I thank you for your attention. I would be available for answers to your questions.
Thank you, Marcello. And at least the last presentation is estimation of a multi-temporal dry deposition of air pollution by urban forest at city scale. The speaker is Davide Travaglini from University of Florence. I remember you.
Thank you.
The question, can you write in the chat box, okay? Davide?
Yes, thank you, Giuseppina, for the introduction. Let me see if you, let me know if you see my presentation, please.
Yes, yes.
Yes,
okay.
yes, okay.
Thank you. Okay, good morning. My name is Davide Travaglini. I work at the University of Florence. And as you can see, this study has been carried out with colleagues from University of Florence, University of Molise, and the University of Tuscia. My talk is on the estimation of dry deposition of air pollution by urban forest. We know that air pollution is a major problem in many cities worldwide, and urban forests provide many ecosystem services that are important for human well-being, like temperature regulation, as presented before by other speaker, and recreation, but also for air pollution removal. Several studies has been carried out in different cities to understand the potential of urban forests to reduce the amount of pollution in the air. One of the most common model used to do this estimation is AIT Eco model. Anyway, many of these models use 2 main forest structural variables to do this estimation, that are the forest canopy cover, and the leaf area index estimation. In 2017, we published a previous work on this topic using Florence as a study area. And in that studies, we used a regression model between field measurement of the leaf area index carried out with the LICOR instrument and airborne laser scanning metrics in order to create a regression model to estimate the spatial distribution of the leaf area index. This study, the study that I'm going to present today, is a continuation of that work. And the objective of this study is to investigate the use of two airborne laser scanning datasets to estimate changes in the dry deposition of particulate matter by urban forests. We did this estimation for 2 years, for the years 2015 and for the year 2018, and we used again city as the city of Florence has a case study. We work in all the area of the municipality of Florence. The total area, as you can see, is around 100 square kilometers, and the urban forest area is more or less the 10% of the total area. As for the forest type, the most common are deciduous broadleaf forest, mainly dominated by quercus species, but there are also mixed forests composed by a mixture of conifers, deciduous, and evergreen broadleaves. This is the list of the data that we have used to do the estimation, the assessment of the air pollution removal for the 2 years, 2015 and 2018. As for the remote sensing data, we use digital orthophotos. Then we use 2 airborne laser scanning datasets that were available for the entire municipality. And from this dataset, we use the digital terrain model and the digital surface model to derive the canopy height model, that is a layer that provides information regarding the height of the forest. The canopy height model had a spatial resolution of 1 meter. Then we used the monthly pollution data that were recorded in 5 ground monitoring stations located inside the city for the 2 years. And in the graphs, you can see the trend of the distribution of the monthly pollution data. And in addition, we used 2 products that were created in the studies that we published in 2017, that are the urban forest type map. This map was created by photo interpretation of the digital orthophotos using the FIO forest definition. We use a classification composed by 7 different forest types. You can see the list of the forest type here in the table, and the distribution of this forest type for the year 2015 in the image. And then we used the leaf area index map that was created in the study we did in 2017. And as I said before, the leaf area index for the year 2013 was created using a regression model between field measurement of the leaf area index and airborne laser scanning metrics. And in the image below, you can see the spatial distribution of the leaf area index for the year 2015. Well, regarding the data elaboration, the method we used, first of all, we updated the forest time map for the year 2018, again by visual interpretation of the digital orthophotos. Then we converted the urban forest time map for the 2 dates in a grid format with the same spatial resolution of the line map. And then we estimated for each pixel of the forest, we estimated the forest canopy cover using the information provided by the canopy height model. Then we create a regression model for light estimation, for the leaf area index estimation, using the forest canopy cover as predictor variable. So here in this graph, you can see the model that we use to assess the leaf area index for the 2015 and for the 2018. And the model described the relationship between the canopy cover, expressed in percent, and the leaf area index that was estimated for the years 2015 by the study that we published in 2017. Then finally, we modeled the pollution deposition before we used models to estimate the pollution deposition at the leaf level using an equation that is frequently used in the literature. For the deciduous species, we considered that the growing season was between April and September, while for the evergreen species, we considered that the growing season was for all the years. Then we modeled the air pollution removal at city scale for each forest type as product between the leaf unit, deposition, the area covered by the forest type, and the spatial distribution of the leaf area index. So now I'm going to report the results of our study. As for the spatial distribution and composition of the urban forest type, we can say that we did not observe special changes between the two data. So the total area of the urban forest increased by just less than 1% in the examined period. Here you can see the graph that shows the agreement between the lie estimated in the study that we published in 2017 and the lie predicted in this study using the exponential model based on the canopy cover of the based on the canopy cover as predictor variable. In this slide, I report information regarding the amount of pollution that has been removed by the urban forest in the 2 years. So in the graph on the left side, you can see the distribution of the monthly total of pollution removal per unit area of the urban forest. And as you can see, the trend of the distribution follows more or less the trend of the amount of pollution that was registered, collected in the ground monitoring station. In the table here on the right side, you can see for each forest type the removal rate that was estimated and the total amount of PM removed by each forest type, let's say, for the 2 dates. As expected, the evergreen species like the conifers and the evergreen broadleaves had a higher removal rate respect to the deciduous broadleaves. And in terms of total removal, you can see that in 2015, the removal was 100, more or less 170. This date, as you can see, is very similar to the amount that was estimated in the previous studies that we published in 2017, while in 2018, the amount of the annual removal is less than in 2000, less than that estimated for the years 2015. In the image below, you can see the spatial distribution of the PM removal for the two years. So our results show that in 2018, the amount of PM has reduced more or less by 23% compared to the year 2015. And this reduction can be explained by different factors. One of these is that in 2018, the monitoring station reports a lower amount of PM in the air respect to the amount that was recorded in 2015. Another explanation could be the forest changes occurred due to disturbances, both in terms of natural or human-induced disturbances. These disturbances, let's say, reduces the amount of the canopy cover of the forest. As you can see in this image I reported below, for instance, this is the effect of a forest cut carried out in a coppice forest. So after the cut, the canopy cover has been reduced, so the potential removal of the forest is less than before the cut. But also natural disturbances like windstorm that have occurred during the examined period have influenced the amount of pollutant that has been removed for the 2018. Here I reported just an example of what was the situation in terms of canopy cover in the area of in a park located in the south part of the city of Florence before a windstorm that occurred in 2015 and after the wind. So you can see that, of course, the canopy cover has reduced due to the wind damages. So I'm going to conclude. As general conclusion, we can say that the forest canopy cover is a good predictor for life estimation, as is already reported in other study, that airborne laser scanning data can be used to estimate the canopy cover at city scale. And I think our study demonstrate that if we get a good model between lie and canopy cover, the model can be extended itself to assess multi-temporal lie values using canopy cover derived from remote sensing product, like the airborne laser scanning data, but we can use also other remote sensing product to estimate the canopy cover in different years. So thank you for your attention. And I'd like also to thank you, Valeria Fanara, which is one of the colleagues she did most of the work that I presented in my talk. Thank you.
Thank you, Davide. And we have 15 minutes for the question. So I asked you, there are a question for the speakers. I have one question for Niam. Niam? Okay. Okay, very interesting your study. And the first question is what accuracy is needed for studies of this type? Because you used 3 types of methodologies: drone, laser scanner, terrestrial laser scanner, and another method. Which accuracy you need to?
You're not looking for centimeter accuracy with this. It's really just to complement the other information that you have about these contributory factors. So, for example, knowing where the street furniture is located, that can give an indicator that this is where cyclist collisions are occurring, or this is a problem for cyclists. So if it's within the nearest 20 centimeters, 10 centimeters, that will be fine. So for the comparison of the different laser scans, it was more to see what kind of information could be taken from them that could be used in this type of assessment, safety assessment.
Okay, thank you. And another question, your study involved only one area across, but you think that is the municipality wanted to extend the study for all city, or
what my study is showing is that if there's different parts of the network, the transport network, and there's certain areas where this type of study is required, and this can be down to visibility, you know, that drivers don't see cyclists, and that's a big one. Failed but didn't see the cyclist, and that's where the visibility analysis is important. It's also the research, the literature will show that a lot of these collisions occur where a car is coming from a secondary road and a cyclist is cycling along a major road, and the car goes straight into the major road and doesn't see the cyclist. So I'm looking to see, can this visibility analysis be able to see these type of events, and perhaps, you know, as they do in Denmark and the Netherlands, when they see this, they change the geometry of the road to make it safe for cyclists. At the end of the day, it's an urban environment. We're talking in these presentations, which are really interesting, about tree canopies and the impact they have on providing for climate, changing the way people commute, you know, to sustainable methods of travel. So cycling is so important. And in this city, you know, 70% of cyclists are male, 30% female. So it's really to get that underrepresented group out there cycling. So it's to provide a safer environment. So the geometry may need to be changed. I hope this answers your question.
Thank you. Thank you. There are other questions? If you want to speak or not writing. If there aren't questions, can we close the session? Titi?
Yes, thank you.
Olivia, okay.
Okay. Thank you. Very, very sharp and very correct information for this different application, but very comprehensive of several information and very useful. So that just to a final remind, because I too remind you that you can see the screen. There is already available on the IT website the second volume of trends in Earth observation from this conference, and it's comprehensive of 7 thematic chapters, and include 45 full paper that accepted the publication. And we have to thank to the Patrizia Rossi, Maria Teresa Melis, and Maria Antonietta De Sena for their competence and effort. Thank you so much. So look at our site.
Okay. So thank you all speakers, and good lunch, and bye-bye.
Only one thing, Giuseppina, only to give some information for the next session. You are invited to participate to the poster session from 13 to 2:30, and to the course that will be done after the poster session. Practically, you have to come back in the main room, and the parallels room, we will use only the parallels room in the parallel panels in the afternoon. Thank you to all. Thank you, Giuseppina, for your participation. Thank you to the speakers for the very interesting session, and see you in the poster session. Bye-bye.
Thank you very much.
Bye.
Bye.
Thank you. Bye.
Bye, everybody.